Imagine you spray perfume into the air. Within minutes, its fragrance spreads throughout the entire room. But have you ever seen those perfume molecules gather back together and return to the bottle on their own? Never. Drop an ice cube into water. The ice melts naturally. But have you ever watched warm water spontaneously freeze into an ice cube without a refrigerator? Again, the answer is no. Both processes obey the first law of thermodynamics perfectly. Energy is conserved in both cases. So why does one happen naturally and the other simply never does? Welcome back to Decoding Education. I'm going to answer that question by decoding the one law of physics that even Einstein said held the supreme position among the laws of nature, the second law of thermodynamics, and the strange, powerful idea behind it, entropy. But before we talk about entropy, let's look at something you've probably witnessed thousands of times without ever questioning it. A hot cup of tea always cools down. A stretched rubber band snaps back when released. These events feel so ordinary that we rarely stop to ask why they always happen in this direction, and never the reverse. This simple observation reveals one of the deepest rules of our universe. In thermodynamics, any process that occurs naturally, without requiring continuous external intervention, is called a spontaneous process. The word spontaneous doesn't mean the process happens instantly or explosively. It simply means that once the right conditions are present, the process has a natural tendency to proceed on its own. For example, if you place a hot metal rod in contact with a cold one, heat automatically flows from the hotter rod to the colder rod. Nobody has to force that transfer. It happens naturally. A compressed spring expands when released. Water stored behind a dam flows downhill once the gate is opened. An iron nail left outside slowly rusts over time. All of these are examples of spontaneous processes because nature drives them in that direction. Now let's look at the opposite. Can heat spontaneously flow from a colder object to a hotter one? Can a rusted iron nail suddenly turn back into pure, shiny iron just by sitting on a table? Can water at the bottom of a waterfall gather itself and flow back to the top without a pump? Of course not. These changes don't occur naturally. To make them happen, we must continuously supply energy from the outside. Such processes are known as non-spontaneous processes. Let's take the example of a refrigerator. Heat naturally wants to flow from a hot object to a cold one. But inside a refrigerator, heat is forced to move from the cold compartment to the warmer surroundings. This is the opposite of nature's preferred direction, so the refrigerator must consume electrical energy every second to make it happen. The same principle applies when we pump water uphill or charge a battery. These are all non-spontaneous processes because they require a constant input of external energy. But this raises a fascinating question. How does nature decide which direction is preferred? Why does heat always choose one direction? Why does every spontaneous process seem to move only one way? Scientists struggled with these questions for decades. The answer turned out to be a completely new physical quantity, one that doesn't measure energy, force, or temperature. That quantity is called entropy, denoted by S. And once you understand entropy, you'll realize that the second law of thermodynamics isn't just another equation. It explains why time itself seems to have a direction. But here's something surprising. When most people hear the word entropy, they immediately think of disorder or chaos. You might have heard statements like, entropy is a measure of disorder. While that idea isn't entirely wrong, it's also not the complete picture. In fact, relying only on that definition often creates more confusion than understanding. So what exactly is entropy? To answer that, we need to zoom in far beyond what our eyes can see, into the microscopic world of atoms and molecules. Every object around us is made up of an unimaginably large number of tiny particles. These particles are never at rest. They are constantly moving, vibrating, rotating, and colliding with one another. Now comes the fascinating part. Even when an object looks exactly the same from the outside, its molecules can be arranged in an enormous number of different ways on the inside. Physicists call each of these possible molecular arrangements a microstate. And what we observe from the outside, things like temperature, pressure, and volume, is called the macrostate. Here's the key idea. A single macrostate can correspond to millions, billions, or even trillions upon trillions of different microstates. Let's make this easier to visualize with a simple example. Imagine flipping 10 coins. There's only one way to get all 10 heads, a perfectly ordered arrangement. But there are hundreds of different combinations that produce a roughly even mix of heads and tails. Now consider that each coin represents an atom. Every possible arrangement of those coins is called a microstate. With just 10 atoms, the number of possible microstates is already quite large. As the number of atoms grows from 10 to millions and then to trillions upon trillions, the number of possible arrangements explodes beyond imagination. As a result, disordered states simply far outnumber ordered ones. Nature doesn't have a preference for disorder. It's simply following probability. Since there are overwhelmingly more disordered microstates than ordered ones, a system naturally moves toward the arrangement that can happen in the greatest number of ways. The greater the number of possible microstates, the greater the entropy. So entropy isn't really measuring messiness. It's measuring how many different ways a system can exist while still appearing exactly the same from the outside. And that's a much deeper and more precise definition than simply calling entropy disorder. At this point, you might be wondering, if disorder is really just a matter of probability, can we actually measure it? The answer is yes. In the late 1800s, the Austrian physicist Ludwig Boltzmann asked a much deeper question. What is entropy at the microscopic level? His answer was so profound that it's engraved on his tombstone in Vienna. S equals K times the natural logarithm over W. Here, S represents the entropy of the system, K is Boltzmann's constant, and W represents the number of possible microstates, the different microscopic arrangements of atoms and molecules that all produce the same observable or macroscopic state. This equation reveals a remarkable truth. The greater the number of possible microstates, the greater the entropy. Boltzmann's equation gave us a microscopic understanding of entropy by looking at the invisible world of atoms and molecules. But here's the practical challenge. We can't count the microstates of billions upon billions of molecules in a real system. So how do scientists actually calculate entropy in experiments? To answer that question, we shift from the microscopic world to the macroscopic world, the world of measurable quantities like heat and temperature. This is where the German physicist Rudolf Clausius introduced the macroscopic definition of entropy. The change in entropy is given by heat over Kelvin temperature for a reversible process. This equation tells us that the amount of that change in entropy depends on both the heat transferred and the temperature at which the transfer occurs. Clausius showed us how entropy changes by connecting it with heat transfer and temperature at macroscopic level, while Boltzmann explained why entropy exists by looking at the microscopic behavior of atoms and molecules. So now we've explored entropy from two different perspectives, but understanding entropy isn't the end of the story. The real question is, how does entropy determine the direction in which natural processes occur? The answer lies in one of the most profound principles of physics, the second law of thermodynamics. It can be stated in many different ways. One of the most common statements is, the total entropy of an isolated system never decreases. It either increases or, in an ideal reversible process, remains constant. This law actually has a few classic versions. The Clausius statement says heat cannot spontaneously flow from a colder body to a hotter body. That's why your fridge needs electricity to pump heat out. It doesn't happen on its own. The Kelvin-Planck statement says it's impossible to build an engine that converts heat completely into work with no other effect. Some energy is always lost as unusable, low-grade heat. At first, these statements may sound complicated, but the idea behind it is surprisingly simple. The change in entropy of the universe will be zero for any reversible process where the universe is understood to mean the system plus surroundings. However, no process is truly reversible, so we should rather say that the change in entropy of the universe for any spontaneous process will be greater than zero, or for any spontaneous process the entropy of the universe always increasing, which is another common articulation of the second law. Let's test this with an ice cube placed on a warm table. Heat flows from the warmer air into the colder ice, the ice melts, and the neatly arranged water molecules in the solid lattice become a disordered liquid. entropy goes up. You will never see a puddle spontaneously freeze into a perfect ice cube on a warm table. That would mean entropy decreasing on its own, and the second law forbids it. Take your car's engine. No matter how well engineered it is, it can never convert all the chemical energy in fuel into pure, useful motion. Some energy always escapes as waste heat through the exhaust and radiator. That lost efficiency isn't bad engineering. It's the second law, non-negotiable. In fact, some physicists argue that entropy is the very reason we experience time moving forward at all. We remember the past, not the future, because the past had lower entropy. This one-way climb of entropy across the universe is sometimes called the arrow of time. So, let's bring it all together before we wrap up. Entropy is a measure of disorder or randomness in a system. At the microscopic level, Boltzmann showed us that disordered arrangements vastly outnumber ordered ones. And the second law of thermodynamics tells us that the total entropy of an isolated system, and really of the universe, can never decrease. It either increases or, in an idealized reversible process, stays constant. So next time you see a broken glass, melting ice, or your suspiciously messy room, you're not just seeing an accident. You're watching the second law of thermodynamics in action. But our journey through thermodynamics isn't over yet, because there are still many questions. If entropy keeps changing during every natural process, what is its lowest possible value? Can entropy ever become exactly zero? The answers lie in the third law of thermodynamics, where we'll explore the strange and fascinating world of near absolute zero temperatures in next episode. Until then, if this video made entropy finally click for you, hit like, subscribe to Decoding Education, and turn on notifications so you don't miss it. I'll see you in the next episode. Keep asking questions. Keep exploring.